Hello, welcome to episode 5 of Multivariable Physics, and today we're gonna finally start wrapping up. We still got one more episode before we can finally wrap up differentiation, multivariable differentiation, and then maybe do some physics stuff now. But so first off, we have a few things to talk about. One is tangent lines, okay, and then the other one is linear approximations. You might not get to that in this episode. So the first thing we want to think about with tangent lines is, what can we do with tangent lines in multiple variables? What does that mean exactly? So to answer this, let's think about this function f x y, right? And we have obviously some surface, we have some surface here in this plane, and we have an x, or we're gonna have some point here, okay? It's gonna be this vector r, and then this is just equal to a b f of a b, right? F of a b. And so what you can think about that is you can think of this as like there's some vector a here, a, right? And so you have a and then b and then y. This might, yeah. So that might be a bit confusing, but just notice that we have this point somewhere on this plane, okay? So we have an a, x is our a, y is our b, and we take some point on that, okay? So what is the tangent line at this point? So I'm going to give you some time to think about it. But one thing you might realize is it's the same intuition with what we did with our, if you remember, with our partial derivatives, right? We have a line this way and we have a line this way, right? And if you remember in calculus we have a line. The tangent line to that is, the tangent line is f prime of a, right? If f prime of a is that's the slope of the tangent line. And so it's pretty much the exact same, except here we have two slopes. We have the slope f of, so we have one slope, f of x b, and f of y of a y, so that's we have two of these, f of y, f of x, two slopes here. And so we can form two tangent lines from this. So we can form one line here. This is going to be a line x. We can form another line here. It's going to be line y. Right? So we don't have one tangent, we have two tangent lines. And if you remember in linear algebra, if we have two tangent lines, or if we have two lines, sorry, we can form a plane between those lines by taking Lx, Ly. We can form a line between those planes by taking, so here's our plane P. P is simply Ly cross Lx. We can form this tangent line, and we have the normal to this tangent line here, right? This normal vector. If you're unfamiliar with that, you might want to review some linear algebra stuff. But yeah, so we take this cross product, and I might have this backwards. I'm pretty sure it's Lx, Ly. Yeah. So we can take that, and what are we going to get if we do this? Well, this is going to give us 1 minus f of x at AB and minus f of y at AB. That's going to be our thing. And actually, this might not make sense. That's because I actually forgot to parameterize or say what Lx is. Lx is just well, 1, 0, f of x of a, and then ly is pretty much the same. It's 0, 1 of f of y at a. And then remember, right, and then a is going to be so I'm sorry, I forgot to parameterize that. But once we have this, we take its cross product, and I hope you can try this out for yourself, but you're going to find that this is what we get, and this is going to be equal to, you know, our normal, this is going to be equal to n hat, sort of, not really, but you know, what we still also have to consider is actually this point, you know, the normal vector n is going to be here. So we want to think about the normal vector to this plane. And this is just going to be this cross product. So this is the normal vector of the plane. So we get the normal vector of the plane, and then we have to add r. Does that make sense? So normal to f is equal to r plus normal of this plane times t, right? Because we're parameterizing this. So this is actually going to be equal to, if you remember r, this is going to be a, b, f of a, b, or I'm going to just write f of a plus minus f of x at a minus f of y at a and 1 times t. And right, and so this becomes our plane, or the normal vector to our plane. And what we actually have here is we have, I'm gonna condense this into this form, f of a, or a f of a, and then plus negative gradient of f of a 1. Okay, so I'm just going to condense this form, because really that's what this is. This is the negative gradient. And so that's how you can get that normal vector. Now we got to think about using this. So to kind of take advantage of this, like how is this useful? What does this even give us? Right? We want to remember this equation. So if you recall, okay, if we have a plane, okay, we have a vector going, oops, we have a vector a, b, c, okay, a plane goes through this vector, and the normal vector to this plane is p, q, r. Then we have this formula to combine them, and that is p x minus a plus q y minus b plus c z minus r equals 0. And we actually have, this is exactly what we have right here, right? This is our plane, this is our normal, this is our r. This is r, right? This is that r that I talked about here. This normal vector, this is what I have here, right? So we can actually use this formula and combine them. And so this is going to give us this equation. I have it down here. So if we actually turn this guy into this guy, we're going to get minus f of x time, or at a. I'm gonna omit the a's, but these are all evaluated at a, minus x minus a. Sorry, x minus a minus f of y minus b plus z minus f, right, equals 0. That's what we get. And remember, anytime I use f, that I actually do mean f of a. And so what can we do with this? Well, we can actually solve for z. Oops, I wanted a better color. This is yellow. Z is equal to f of a plus f of x of a, x minus a, plus f of y of a, y minus b, right? So you get this interesting equation. And if you remember with when I talked about the chain rule with the gradient, stuff like that, we took a sum of where we had partial derivatives and we turned that into a dot product. We can do the exact same thing here, because this is actually the dot product of f of x, f of y, at a, dotted with x minus a, y minus b. So we can actually think about this as, well, this is just the vector x, right, minus the vector a, and this is just the gradient of f at a, evaluated at a, right? That's all that is. So we can actually condense this thing into z equals f at a plus the gradient of f at a dot x minus a. And if this looks familiar, that's because this is the, if you're familiar with this is the way we can get this equation. This is f equals a plus f prime of a x minus, I'm going to actually just go back just a bit and then write it up higher, y equals f of a plus f prime of a x minus a. That is the line y. That's the equation for the tangent line. This is the equation for the tangent line when x is one dimension. This is the same thing. That's exactly the same thing. The only difference is that we actually have a tangent plane instead of a tangent line. And then in higher dimensions, it's not exactly a plane. It's called a hyper. It's like hyperplane over some manifold. But that's not important. We don't need to know what the hell that doesn't matter. You don't need to know what that means. But yeah, tangent plane. At f of a. This is the takeaway. You kind of want to know this is going to come in handy when you actually start talking about linear approximations to multivariable functions, and then I promise we're going to actually start doing some physics. So see you then.